Hi everyone, thank you for joining today. I'm excited to walk you through a recent ACL 2024 paper titled Active Prompting with Chain of Thought for Large Language Models. The title highlights its two main ideas: actively picking the model's difficult questions and using chain of thought examples to guide it. Let's dive in. Here's a quick look at today's outline. I'll start with a brief summary of the paper, then cover some preliminaries on how prompts are typically used. Next, I'll explain the motivation behind active prompting, dive into the method itself, and go over our experimental setup and results. Finally, we'll conclude and explore conclusion and application to medical Q&A, discussing how to adapt these ideas to our own medical question answering tasks. On this summary slide, we answer three key questions. Why do we need active prompting? When we ask an LLM to solve problems with just a few examples. The choice of examples typically relies on human intuition. If those examples are poor or unrepresentative, the model can get confused and fail to solve new problems. Active prompting instead taps into the model's own signals, its uncertainty to identify which questions it struggles with, and select better prompts. What are the benefits? By active prompting, we force the model to select the hardest questions, the ones it finds most ambiguous. Then, by giving clear examples for those hard questions, we teach the model how to solve similar problems more easily, leading to consistent accuracy gains over previous methods. How can we use this idea in our case? In our medical Q&A training, we've been hunting for higher quality training data. This active prompting approach helps us pick out the questions the model struggles with, those high uncertainty cases, and focus learning on those tricky areas. Prompts can be applied at either the training stage or the inference stage to enhance LLM performance. In training phase, prompts here actually adjust model parameters, directly improving task comprehension and generalization. In inference phase, prompts supply hints or examples to a frozen, pre-trained model, boosting performance without any retraining. Today, our focus will be on leveraging prompts during the inference stage to enhance LM performance. Now, let's look at how prompts are used during inference. Prompt here means instant tutorials. How can we use prompts during inference? We provide task-relevant example and question-answer pairs as prompts. Think of a prompt as a sort of an instruction manual for LLM, such as, here's how to solve this kind of problem and how you should answer it. The LLM reads that instruction and generates an answer for the new question, applying the same rule. At the bottom, you can see an example of standard prompting. In the model input, we first show a prompt, which is a QA pair. For question, Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? For answer, the answer is 11. Then comes the target test question LLM solves. Q, the cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? In the model output, the LLM answers. A, the answer is 27. But the answer is wrong. This shows a limitation of standard prompting. Let's look at another way prompts can be used. We use chain of thought instead of simple prompts. Chain of thought, or COT, is a method where the prompt includes the step-by-step reasoning process, not just the final answer. So the model follows that same reasoning process when solving new problems. At the bottom, you can see an example of chain of thought prompting. In the model input, we first show a prompt, which is a QCOTA pair. Question is same as the standard prompt, but for the answer, the reasoning process is added. So for answer, Roger started with 5 balls. 2 cans of 3 tennis balls, each is 6 tennis balls. 5 plus 6 equals 11. The answer is 11. Is provided as a prompt. Then comes the target test question LLM solves. In the model output, the LLM answers. The cafeteria had 23 apples originally. They used 20 to make lunch. So they had 23 minus 20 equals 3. They bought 6 more apples, so they have 3 plus 6 equals 9. The answer is 9. This time, the model gets the correct answer with reasoning process also, thanks to chain of thought prompting. Chain of thought is powerful, but there are limitations of chain of thought approaches. The main issue is that these methods rely on fixed examples and unclear selection rules. Typically, 4 to 8 COT examples written by humans are reused over and over again, but there's no guarantee of working well across different tasks or types. In fact, performance can degrade if mismatched. Also, there's no clear rule or guideline for which examples are most helpful. So the selection relies on human intuition or randomness, which makes annotation inefficient and inconsistent. These are the examples across 3 tasks. First, in math word problems, the model must read the problem in everyday language and perform the correct arithmetic operations. Second, in CSQA, common sense QA, the model has to apply background knowledge to choose the most appropriate answer from multiple choices. Third, in last letter concatenation, the model measures basic logical and string manipulation skills like extracting the last letter of each word and concatenating the results in order. As we can see, these are very different task types. So a small fixed set of COT prompts may not work equally well for all of them. Chain of thought also shows vulnerability to task diversity. Even within the same math task, the required reasoning patterns differ depending on whether it's freeform, multiple choice, or open-ended. So a single COT set cannot cover all task types. This leads to risk of bias or incorrect answers. We see this clearly in 2 math word problems below. On the left, a free response question asks how many tennis balls Roger has. The reasoning is straightforward. 5 plus 6 equals 11. On the right, a multiple choice question asks how many keystrokes are needed to type numbers from 1 to 500. The reasoning is more complex, using digit counts from 1 to 500, and the answer is option B, 1392. So now the question is, what does this paper propose as an active prompting method? It suggests selecting the questions that the model is most uncertain about and having a human annotate only those few questions with COT reasoning to update the prompt. This is called the active prompt. With just a small number of examples added during inference, this method can achieve higher relevance and better performance. The key idea of active prompting is to use task-specific exemplars in prompts instead of reusing fixed exemplars. Exemplars here mean typical or representative examples. So which examples actually help an LLM solve problems effectively? We pick the questions that the model struggles to answer confidently. In other words, those with high uncertainty, meaning its answers vary when the same question is asked multiple times. These high uncertainty questions reveal the model's weak points or blind spots. Therefore, we select questions with high uncertainty first and then provide them with chain of thought examples. To measure uncertainty, we use 2 intuitive indicators, disagreement and entropy. Before diving into the details, let's walk through the overall framework. Step 1 is uncertainty estimation. For every question in our unlabeled pool, we generate k numbers of answers for each question using COT-style format. Then use disagreement or entropy formula to compute uncertainty score for each question, so we know which questions the model finds most confusing. Moving on to step 2, selection. Here, we take our uncertainty scores and rank every question in the pool. Then we select the top n most uncertain questions for annotation. Step 3 is annotation. For each of the top n most uncertain questions we selected in step 2, human annotators write full chain of thought reasoning plus the final answers to create a new exemplar set E. Step 4 is inference. Here, we take our new exemplar set E as the few-shot COT examples and simply prepend new exemplars E to every test question. With E in front, the model applies those task-specific exemplars to guide its reasoning and generate answers for all the test instances. Now, we will describe the framework in step-by-step starting from the uncertainty estimation by using few-shot COT and zero-shot COT. Here's how Step 1, Uncertainty Estimation works in overview. This is a step where we generate k numbers of COT answers for each unlabeled question. We generate answers using the COT reasoning format in two ways. Few-shot COT is used when we already have human annotated exemplars to guide the model's reasoning. Zero-shot COT is used when no exemplars exist. We simply add, "Let's think step by step," so the model self guides its own chain of thought. These k-generated answers form the answer pool for uncertainty estimation. Let's find out in more detail about the two styles used for the COT reasoning format. Using few-shot COT, a few numbers of QCOTA exemplars are added. For example, Q, there are 15 trees in the grove and so on. And the answer is A, there were 15 originally. Then there were 21 after some more were planted. So 21 minus 15 equals 6. The answer is 6. This teaches the model follow the same step-by-step reasoning process when solving new questions. In zero-shot COT, no examples are given and simply the prompt starts with a sentence like, "Let's think step by step." The model then tries to generate its own chain of thought reasoning steps to reach the final answer by itself. On this final step of uncertainty estimation, we estimate how uncertain the model is by computing uncertainty score for each question based on the answer pool. In here, uncertainty means lack of consistency against final answers, even if when the same question is answered. In the right side, there is an example of how we put those two metrics into action, using the tennis ball question as our running example. If k equals 5 times, we prompt the model for 5 times of answering with question number 101 and collect its 5 final answers for uncertainty scoring. Two measurement methods are used for uncertainty score estimation: disagreement and entropy. Disagreement is computed by counting the number of unique answers dividing with k. With the example Q101, the uncertainty score will be 1.0, because in the middle panel we got 1, 2, 3, 4, 5, so that's 5 distinct values. So the disagreement value will be 5 divided by 5 equals 1.0, and a score of 1.0 means complete disagreement because every run gave a different answer. By contrast, look at the top panel. All k equals 5 returns 3. So disagreement value can be calculated as 1 distinct answer divided by 5 equals 0.2. In this case, the disagreement is very low, which means agreement score is high. Another measurement method is using entropy. Entropy measures how disordered the frequency distribution of the answers are. For each unique answer AJ, entropy is computed by how many times that particular answer AJ appears among the K outputs for question QI. So its frequency is computed by count AJ divided by K. Let's look at the middle panel again. If we apply entropy scoring into this middle panel, here, each of the 5 answers appeared exactly once, so each has probability of 1/5. Then when applied to the usual entropy formula, because the probabilities are evenly spread as every answers are same, the entropy hits its maximum, signaling high uncertainty, which means that the answers are inconsistent. In this way, questions with a wide disordered answer spread get flagged as highly uncertain, exactly what we need for active prompting's selection step. Based on the uncertainty scores computed in Step 1, we rank all unlabeled questions in descending order of uncertainty and select the top-end questions and pass them on for annotation. Questions with the highest uncertainty like red box Q, where the model's answers were all different, sit at the top, while those with low uncertainty like blue box Q, where every answer matched, fall to the bottom. Step 3. Annotation. In this step, a human annotator takes the top-end questions from our uncertainty ranking and converts them into COT exemplars, forming the exemplar set E. On the left, you see our most uncertain questions, those that the model struggled with the most. For each one, for example, Q101 and Q691, the annotator writes out the full chain of thought reasoning followed by the final answer. These annotated QCOTA pairs become our new exemplars E, which we'll add to every test question in the next inference step to guide the model's reasoning. Step 4. Inference. We combine our newly annotated QCOTA exemplars with a test question to form a single prompt, then run inference on the test data. First, we add the exemplar set E, the human-written chain of thought examples for our most uncertain questions directly in front of each new test question. Then we feed that concatenated prompt into the model. Because the model sees the full COT reasoning steps, followed by the final answer for each high uncertainty exemplar, it applies the same step-by-step process when solving the test question. Then, how active prompting works. Instead of using a fixed QCOTA example in the prompt, we actively replace it with a QCOTA pair built around a high uncertainty question. In standard COT prompting on the left, you always add the same fixed example no matter what you're asking. With active prompting on the right, we swap in a human-written COT example for the question Q101. The model found most uncertain. At inference time, the model sees this high uncertainty Q101 COT example first, then the new test question. It follows the same reasoning chain and yields more reliable answers. This targeted replacement focuses the model on its blind spots, boosting both accuracy and consistency with very few examples. The experiments cover 3 reasoning categories: arithmetic, common sense, and symbolic. Arithmetic focuses on solving math word problems through logical arithmetic operations, using datasets such as GSM-8K, ASDIV, SVAMP, AQUA, and single equation. Most are free response, with AQUA as multiple choice. As shown on the left, exemplars break down the quantities and show each calculation step in words. Common sense solves problems based on everyday, real-world questions with CSQA and strategy QA. Exemplars here provide brief elimination or inference steps. For instance, Sammy wanted to go to where the people were. Where might he go? And the options are given: and the answer is provided with the reasoning step like the answer must be a place with a lot of people. Symbolic performs logical reasoning by representing knowledge as symbols, exemplified by the last letter concatenation task. Take the last letter of lady, which is he, and the last letter of gaga, which is a. Concatenating them gives ya. The answer is ya. For the evaluations, author compares active prompting against 4 strong baselines: COT, SC, auto-COT, random COT. Chain of thought uses a fixed set of 4 to 8 human-written QCOTA exemplars, adds to each test question, followed by a single decode to produce an answer. Self-consistency samples the same question multiple times under the COT setup to generate several reasoning paths and selects the most frequent answer. Auto-COT clusters test or development questions to identify representative prompts, then generates one zero-shot COT exemplar with let's think step by step, and combines them into a single prompt. Random COT matches active prompting's annotation budget, but chooses questions at random for human COT annotation instead of using uncertainty. By benchmarking against these methods, we show how targeted, uncertainty-driven exemplar selection paired with human-crafted COT prompts drives improvements in both accuracy and robustness. In their experiments, the authors evaluate 2 GPT-3 variants. Text DaVinci 002 is an instruction-tuned GPT-3 model that excels at natural language understanding, generation, and question answering. It reliably follows both few-shot and zero-shot COT prompts. Code DaVinci 002 is a model pre-trained on GPT-3 and natural language. Its strength in procedural and mathematical reasoning yields especially high performance on complex, step-by-step prompts. Both models are used purely in an in-context setting, without any additional fine-tuning. For uncertainty estimation, the authors randomly sample 1,000 examples from each dataset and set the number of repeated COT generations, K to 10. They report exact match accuracy on the held-out test sets as the primary evaluation metric. Notice that the blue bars for active prompt D exceed the yellow bars for self-consistency in almost every column. On Text DaVinci 002, the average accuracy jumps by 7.0 points, from 67.9% to 74.9%. And on Code DaVinci 002, it increases by 1.8 points from 79.1% to 80.9%. The biggest improvements occur on GSM-AK, AQUA, and last letter concatenation. In other words, actively selecting high uncertainty questions as exemplars consistently boosts performance compared to self-consistency. Here, K denotes how many times we sample answers for each question to estimate its uncertainty. Across all 3 benchmarks, GSM-AK, ASDIV, and single EQ accuracy steadily rises as K increases, because more samples lead to a better estimate of which questions truly confuse the model. Notice, though, that beyond about K equals 10 highlighted in red, the gains begin to decrease. That tells us K equals 10 strikes a good balance between computational cost and uncertainty estimation quality. Next, let's examine the link between uncertainty and model performance. On all 3 scatter plots, GSM, 8K, ASDIV, and single EQ, we see a clear inverse relationship. Lower uncertainty corresponds to higher accuracy. The blue dots show standard, chain of thought prompting with a fixed exemplar set, while the orange X's show active COT, where we replace those exemplars with high uncertainty question examples. In every case, the active COT points cluster up in the upper left low uncertainty and high accuracy. This confirms that by selecting and using the model's most uncertain questions as exemplars, active prompting effectively reduces uncertainty and in turn raises overall accuracy. Let's wrap up. Active prompting leverages uncertainty to identify the questions the model finds most challenging. By providing clear chain of thought examples for these hard questions, the model learns to solve similar problems more accurately with minimal annotation. So how could we apply this idea to our medical Q&A task? Instead of using it only at inference time, we can bring it into training. First, we could take an AI Hub dataset that's relevant to our benchmark tasks, run our uncertainty estimation over it, and filter out only the high uncertainty samples. Then, we fine-tune the model on that hard case subset to boost consistency and overall performance.